give us a summary of what was done last time. That would be good, I think.
We proved two important theorems.
Right.
So one was about exchange of limits. It was about the condition when the limits can be exchanged.
Right. So let me
So
write that maybe. Exchange of limits. And so you can just mention maybe the condition.
yeah, the condition was that you have got obviously a sequence of functions which converges to a function f. You've got a sequence fn which converges to a function f, and we have to. The theorem is like this: that uh, limit of limit of fn of x as x tends to say x naught, and outside n tends to infinity,
Right.
equals limit of
Yes, this is the
n tends
exchange.
to x naught, right? Yeah, so exchange
Uh-huh.
if and only
Mm-hmm.
if and only if f is continuous.
And any other condition? It may
Mm,
be, you might be implicitly assuming it, so you can say if there is anything else you're assuming.
no, we uh,
On the FIs,
yeah, all of these are continuous as well.
naturally, right? So that is like almost implicit, because otherwise we won't expect F to be continuous, or, yeah, that's will be very strange. So yeah, so these are continuous. So this is the hypothesis, that you have continuous functions and they are converging. So just converging, we are not saying they are converging uniformly or anything. Okay, just converging means that every point you take the limit, and that limit so you fix a point x naught, you take the limit, that is f of x naught, and you fix another point x1, take the limit, that is f of x1. So less like that. Okay, so these are continuous. Okay. So Raghav, do you absorb the statement? I'm not expecting you to prove it now, but do you absorb the statement?
Okay, yes, sir.
Yeah. So maybe Adish, you can tell us like how, like maybe expand on what the left hand side means, right? And if you,
Uh,
uh,
yeah, the left hand side just means that the first inner bracket is just the continuity of fn. So that just becomes fn
no, so I don't
of
want
x.
the proof. Yeah, okay. That's I think that's better even then. Yeah, but not. So So you can tell us. Yeah. So yes, go on. Sorry.
No, you said to elaborate, that's why I'm
Huh.
elaborating.
Yes. No. Go on.
No, the left hand side, the inner limit is just basically saying about the continuity of fn, which is given. So that just becomes fn of x naught.
Ah.
And now the outer limit is obviously it is given that fn converges to f. So the outer limit will obviously be a limit of fn of x naught as n goes to infinity will obviously be f of x naught.
Okay. Okay. Now you. Yeah. So that's good. Yeah. So okay. So what I also wanted to explain is, meaning that, I mean, what does it mean, like, to take these limits, in the sense that, so maybe I can explain the right hand side. I won't explain how you get equality, but just what I'm saying is, uh, so Raghav, you can see that for every x you can take this limit, right? So if you focus on the right hand side, left hand side is clear now. Right hand side, what I'm saying is that for every x you can take a limit, right? So this what this will become when you take the limit for a x, I mean, this will become something, right? And that's something when you do for every x, so it becomes a function of x, right? For every x you take the limit, for another x you take the limit, so it becomes a function of x. Okay, so, and so you can take the limit of that. I'm just saying that how does it make sense? How does each side make sense? Equality, we will see. uh, okay, so the left hand side has been explained. Raghav, if you follow, then you can try to break down the right hand side also similarly. And if you don't follow, then you should tell us, so we can try. Okay. So like, I'll just say the reference side again, right? So see, just because Fn is continuous, this thing just becomes Fn of x naught. Yeah, so do you follow that?
Yes, sir.
Yeah, and then you take the limit of that as n tends to infinity, that f of x, that is f of x naught by. Now I want you to show that the right hand side is also f of x naught. So you can try to do that. Let's see.
First limit will be f of x,
Right.
and because f of x is continuous,
Yes. If f of x is continuous, then this is just
if
f of, sorry, so I've written it wrong. Yeah, then it's correct. Yeah. Okay. So what we have shown is that if f of f is if f is continuous at x naught, whatever, if f is continuous, then we can exchange the limits, right? Because you can see both sides are same. Now for homework, you can show that if you can exchange the limits, then f is continuous. It is equally easy, but you should try to do that on your own. Okay. Like I want you to show from here that f is continuous at x naught. Okay. So please try that. All right. Okay. So now what was the other thing that, so we just a quick recap. So we'll go a little fast here. So Adish, what was the other thing we did? Maybe.
The other thing was that, again, we say that uniform convergence implies that the function to which the sequence of functions converges is continuous.
Okay. So uniform convergence implies, I'll just say limit, because the limit is a function. Limit is, so I'll say also, which implicitly means that the sequence was continuous functions. Sequence of continuous functions is also continuous. Okay. Now, maybe Raghav, you should try to not a proof, but just extrapolate what this means. Proof, I don't expect now. It was a little involved, not difficult, but whatever. What do you understand from here? Uniform convergence, what should be the setting and everything? Try to say in your own words. Then we'll move to today's stuff. Yeah. So I'll try to begin. Okay. So we had the setting. The very basic setting was that we have a sequence of functions. Okay. What functions? These are obviously continuous functions. The also means continuous. So these are continuous functions. And then we are saying uniform convergence, which means that these converge uniformly to f. Okay, uniformly. So you recall the definition of uniform convergence? Yeah, so maybe Adish, if you remember, you can recall the definition of uniform convergence. So maybe each fi is on a certain domain. Some domain. Let's keep it 0 to 1 for now. But no, actually I should not. I'll just keep it any domain E. I'll just keep it any domain E. I mean, so the definition of uniform convergence, if you can just say it in words, and then
Like the entire definition, or just
yes, the definition of uniform convergence. Yeah, or let's say this sequence of functions is defined on a set E. This is also the notation that Rudin uses. Now, what does it mean to say that these converge uniformly to F? Just that. What's the meaning of uniform convergence?
uniform. Yeah, so it means that you can always find an n, a naught. So given for all epsilon, you can always find an n naught, so that fn of x minus f of x, so that distance between them is less than epsilon.
For all n
For
bigger
all
than
x
n naught?
Yeah, for all x.
And for all
Below
x. Yes, right. So there is one n naught that works uniformly for every x. Okay.
It's like a epsilon and not pair.
Yes, yeah. So the n depends on the n naught depends on epsilon, right? So you could say like that, yeah. Okay. So there is one n naught that works, and this just recalling this definition is important because we would like to see where uniform convergence happens, and let's see. So we'll see. So this and then now, Raghav, can you complete the statement? So this is the hypothesis. Then what are we saying? The limit is also continuous. Yeah.
Sir, I didn't understand actually.
Yeah, no problem. So let's um yeah, so let's take an example. Let's just take an example, right? So let's take E to be, let's take E to be 0 to 1, open 0 to 1. Okay. And let's take Fn to be x to just the simple example. So x to the n. Now, first of all, what should f be in this case?
Limit.
Yeah, f is the limit. So what's the definition of f? What would be f of x naught for some x naught? So you have to
Maybe
compute
1.
the no. So see, try to see. So for every x naught, you have to figure out the limit. Right. So you fix x. So the method is this, right? I mean, the basic definition is this. Whether it's uniform or not, that you can check later. That we can think about later. Okay. Yeah, maybe this is not uniform. This is not uniform, maybe. Yeah. But the point is that you take an x naught, right, and you compute the limit. So what should the limit be? Adish, can you tell? Yeah. So
For
just
any x naught, right?
yes, if there is a common thing, then you can say. Otherwise, you can say in what should the limit be?
0.
Right. Yeah. So the limit should be just 0. Right. So that is because yeah. So because for just you take x naught and then you take x naught square and just take this. Where is this going to go? 0. Right. Right. So that is easy, right? So f is just 0. Now, is the convergence uniform? But is the convergence uniform? So from here, we will better understand the definition. So let's see.
The meeting is going to end.
Yeah, so let's just decide whether this is uniform or not quickly. Yeah, because the meeting was standing for a long time. Maybe some guess. So I'll tell you the convergence is not uniform, and now you give me a proof after the meet. I'll launch the meeting again.
Did
Okay.
we do this last time because there exists no I guess the supremum or the infimum is one or something like that kind of argument was there.
Right. So you can detail the argument then. Maybe just I'll end and start the meeting again. Then you can detail the argument. That will be good. Okay.